Welcome to Challenging Climate, a podcast where we discuss the science, technology, and politics of climate change. I'm Pete Irvin, climate scientist, and Jesse Reynolds is on holiday in the south of France. In this episode, which we recorded before Jesse's holiday, we spoke with Tom Matthews, an associate professor at King's College London, in what may be our most extreme episode to date. We covered his work installing the world's highest ever weather station on top of Mount Everest, his work looking at glaciers, and we discussed the interesting differences between glaciers at the top of the world, the coldest places on the planet, and the glaciers that we see in the tropics that are quite different. And we also talked a lot about extreme heat and its impacts on society, including the study that he published, which identified the first emergence of humid heat too high for humans to survive. It's interesting stuff and a little scary. I thought Tom did a great job explaining the science behind the extremes of heat and cold, and I hope you enjoyed listening as much as we enjoyed recording this episode. Thanks for listening.
We are joined today by Dr. Tom Matthews, who is an associate professor of environmental geography at King's College in London. He studies the drivers of weather and climate extremes, how glaciers are changing in a warming world, and the impact of climate change on society. Tom, welcome to Challenging Climate.
Thank you very much, Jesse. Good to be here.
We'd like to begin with a sort of an open question. Tell us about your background, how you ended up being an environmental geographer and examining glaciers and heat extreme. What sort of path led you to that point in your career?
It's a good question. As we'll discuss later, my interests do seem pretty different at first. Extreme heat on the one hand and glaciers on the other hand. But my journey started, I grew up in the south of England, long way from any glaciers, but in an educational environment where geography was taught quite well. Went to Ecuador at the age of, I think it was 17, and saw the Andes and the Amazon for the first time, and was really captivated by that experience. And that kind of drove me on to study geography at university. And I didn't go too far. I went to the Midlands of England. I went to a place called Loughborough, and I went there to play sport, actually. I thought it would be a fantastic place to hone my skills as an athlete, known for its sports. I did very, very little sports there, and ended up doing quite a lot more work. I really started to kick on and enjoy my studies in geography. And I took a year abroad in Sweden as part of the Erasmus exchange program. And I noted, because I was in Sweden, that there was a final year field course at my home university in the Arctic in Sweden, looking at glaciers. And I went on that course and absolutely loved it. I just really, really sort of found my niche in geography, I would say. In this final year, went on to do a dissertation in geography. Was in the right place, the right time when offered to do a PhD at Loughborough in glaciers and climate interaction. So I took that path, and then after the PhD, went on to Maynooth University in Ireland. And Maynooth, the expertise there was more in hydroclimatic extremes that affect the British Irish Isles, so storms, how they determine catchment hydrology and drive floods. Flooding is a big challenge or a big hazard in Ireland. So I got more into that side of climate science and worked there for a couple of years, and then came back across to England and worked in Liverpool John Moores University, and then back to Loughborough, actually. Had lectureships in both those positions and continued the work in climate extremes. So I was moved away from glaciers where I started, and I'd moved around sort of climate extremes that affect, let's say, northwestern Europe, mainly focused on hydrological cycles. So storms were my speciality. And then whilst moving between Liverpool and Loughborough, I started to develop this interest in heat. And I had a pretty good background, actually, because glaciers, as we may talk about later, what determines their melt rate is the fluxes of energy at the surface. And that also determines how hot it feels to the human body, is fluxes of energy between the environment, the atmosphere, and our skin. So a lot of overlap. And then I landed in King's College London at the end of 2021. So I've been here about 8 months now. I'm very much still finding my feet, but enjoying life here so far, and continuing on these two themes with glacier climate interactions and extreme weather and climate more generally, with a specialisation there in extreme heat. So that's how I got to here. A bit of a roundabout story, but that's it.
Now, I presume much of your work, like mine, focuses on a desk and a computer and computer simulations and reading and so on. But you've also done some pretty extreme field work. Could you tell us a little bit about, as an expedition, you went up onto Mount Everest? Could you tell us a little more?
Yeah, absolutely. So I actually I sort of missed out a bit of the backstory into why I decided to do a PhD. I decided to do a PhD because I actually was really drawn by the field work. So I've always liked the mountains. As a hobby, I've always done a lot of hiking, some climbing. And when I was an undergraduate, coming towards the end of my studies, I realized that, field work would take you to these remarkable places. So to me, the first place to go to really was the Arctic, the Swedish Arctic. And to go and stand on a glacier, I found that really exciting. So the field work during my PhD was a lot more of the same. I was putting weather stations out on glaciers in the Arctic, so in Sweden and in Iceland, and then measuring the weather and trying to work out how we could better predict glacier melt and glacier mass balance. In other words, the inputs and outputs of mass to a glacier. So snow the input, and melting and sublimation generally the outputs or the losses. But then when I moved to Ireland after the PhD, most of my work was indeed, as you described, mostly desk-based. It was crunching numbers, looking at climate model output, statistical modelling, some physical modelling, that sort of thing. And then after several years of doing that, it was actually a pleasure trip to Ladakh in northern India, where I was due to take part in a half marathon. I say due to take part in a half marathon because I ate something wrong the night before the day of the half marathon and actually spent that day, in a toilet cubicle rather than running. So I didn't do the half marathon, but I was in Ladakh for quite some time, doing some trekking and got to know the area quite well and appreciated the proximity that people were living to the edge with respect to water resources. I mean, it's quite a well-studied region. Glaciers supply a lot of the meltwater to the subsistence farming communities in the region. Glaciers are retreating rapidly, as they are worldwide, but not a huge amount is known as exactly how fast they may retreat. And part of that is because of a lack of basic observations. So I was reminded of my PhD journey and decided to apply for a grant to National Geographic to put out some weather stations in Ladakh on glaciers to get a better understanding of the current climate and how sensitive those ice masses might be to warming. So I was successful, luckily, in applying for that grant. And during my interactions with National Geographic, they alerted me to the prospect of this expedition to Mount Everest. This was this conversation was happening at the back end of 2018. And the expedition was going to go in the spring of 2019. And to cut a long story short, they were short of some glacier-climate people working on that project with expertise in weather stations. So I was called in to join Baker Perry of Appalachian State University in the US to help lead the meteorology component of that expedition. So to design the weather stations and decide what we were going to measure, how we were going to measure it, do things like figure out the type of weather that those sensors would have to endure, or the stations would have to endure, how strong the winds were likely to be, how cold the temperatures were likely to go. So design the stations, then ultimately go out and put the stations in. So we installed a network of 5 weather stations during 2019 as part of this big National Geographic and Rolex perpetual Planet Everest expedition. And they ranged in elevation from Fortsey, being the lowest weather station, where the Khumbu Climbing Centre is located, this remarkable centre that's dedicated its existence to helping the local Sherpa upskill in climbing and guiding skills to make it safer for them to operate on the mountain. And our weather station is co-located with that centre. So there's a bit of kind of precedent for these types of activities in the region to develop local capacity. So that's the lowest station, it's at 3,800 something metres. And then other stations are at Everest Base Camp. That's about 5,300 meters. Next one is Camp 2, and you have to go through the Khumbu Icefall to get there. So that's kind of the cutoff for accessibility. You then have to start climbing to get to Camp 2. This is 6,500-ish meters. And then the next station is up at the South Col. It's about 8,000 meters, or a shade under 8,000 meters. It's the location of the last or highest camp on the Nepalese climbing route before reaching the summit of Everest, so Camp 4. And then the highest station was intended to be very, very close to the summit in 2019. But because of pretty difficult summit nights, very crowded year, because the weather funneled people into just a few days of climbing in 2019, we had to abandon that plan, put the station a bit lower at a spot called the Balcony, which is this large flat area, well named because it does resemble a balcony. You've got a great view up there, relatively flat. And that's where we put our highest station. That's at 8,430 meters. So that was in 2019, and then the 2 highest stations took a bit of a pummeling in between. South Col Station was still standing, but not transmitting data. That was the monsoon of 2021, it stopped transmitting data. And the Balcony Station we found out, knocked down by very strong wind in the winter of 2019-2020. So in 2022, in the spring, so just a month or a couple of months back now, we went back with the same Sherpa team and we repaired the South Col station and put in some new sensors, some fancy new sensors, and also moved that higher station that had failed to its intended location for 2019. And that was this place called the Bishop Rock, which is the highest rock on the Nepalese side, just a shade under the summit there, about 8,810 meters above sea level. So that's the most extreme field work I've done, with these two Everest expeditions. And just real tremendous privilege to get to go to Everest and do that science and to work with the incredible Sherpa teams there that are regularly applying their trade or expertise on the mountain, and working together was really satisfying.
Yeah, how much does a weather station weigh? I presume it's quite, you're going to lift it, you're going to carry it up, or the people are going to carry it up, right?
Yeah, you certainly have to know how much it weighs. That was one of the early, I'd forgotten that step of the planning process, but that was a huge consideration from 2018 through to that first expedition in 2019, was how light can we make the station? So the mast was specially engineered to be super strong, but also super light. All the components, the way weather stations work in general, for those that aren't familiar with them, is essentially they're kind of, they're as big as you want them to be, or they can be as comprehensive as you want them to be. So you need some kind of mast or some kind of tower to affix the instruments to. So we designed that to make it super light and super strong. But then the other sensors, you can add on whichever sensors you want to the station. You need a logger to measure the data that are coming from those sensors. So you need a logger and enclosure to affix onto the mast or the tower that you've got. And then you can add in whichever sensors you like. You plug them into the logger and you also bolt them onto the tripod or the mast. So that's generally what a weather station is. And from our perspective, what we were very keen to do is keep each of those components as light as possible. So where there are options, have the lighter sensor, and also to only measure those things that we really needed to measure in order to keep weight down. The batteries are the heaviest component. And when we added everything together, the weight was about 50 kilograms for the 2019 version. Slightly heavier this year because we added in a few bits. We added in two extra sensors for the highest station, and an extra solar panel. So I think we came in about 60 kilograms at the end, but we were also conscious of the fact that no one person could carry above a certain threshold of weight, because they also, there's the Sherpa, they're carrying the majority of the weight. They also have to carry their personal gear, oxygen tanks. So I think the upper limit that one person could carry was 16 kilograms. And we managed to keep everything to that limit. But of course, some people, one of our brave Sherpa, a very strong Sherpa, still had to carry the mast, which is not that heavy, but it's quite unwieldy. And I'll never forget the Sherpa that was leading the way this year was carrying the mast on his back, and it looked like a flag going up towards the summit at night. So it'll always be ingrained in my memory, was following what looks like in the darkness a flag leading towards the summit. So the weight, was a real consideration, very, very important consideration throughout. And we kept things to about 50 kilograms the first time, 60 kilograms the second time with a few upgrades.
A lot of your work has been in glaciers, as we've mentioned, of course. When I think of a glacier, I'm not sure about other people. I imagine something that terminates at some sort of Norwegian fjord. But some of your work is focused on relatively low latitude glaciers. So let's talk about that for a little bit. I presume, first of all, they have to be at high altitude to compensate for the latitude. It has to be cool enough during the year that it's frozen for a majority of the time. What are some of the other key physical differences between a low latitude glacier and a more typical high latitude one?
Yeah, really, really good question. Ultimately, glaciers are glaciers, in the similarity they all share is that they are indeed comprised of snow and ice. So they look often quite similar when you're on them, but the environment that they're in can be very different. And the characteristics of the accumulations and the snow input and the melting or the ablation more generally, which includes the sublimation of snow, which is like evaporation, but rather than liquid to gas, we go straight from solid to gas. Those processes can occur or have different cadence throughout the year, depending on where you are. So, for example, in high mountain Asia on Everest, you have accumulation and ablation occurring during the monsoon. That's the period of all the activity. Whereas in the higher latitudes and lower altitudes, so the likes of your beautiful Norwegian fjord, you have a clearly defined cold accumulation season where most of the precipitation is snow and the glacier is accumulating mass, and a separate ablation season, the summer, where it's losing mass. They're different in that respect. But perhaps the most obvious starting point that I could lead from your example with is indeed the height that we're talking about, the altitude of the glaciers. So, for example, the Khumbu Glacier, which descends from the upper slopes of Mount Everest, its terminus is at about, so its lowest extent, it's an altitude of about 5,100, 5,200 meters above sea level. Base camp is in the lower reaches, about 5,300 meters above sea level. We also just came back from installing a very high altitude weather station in Peru. So that's in the tropical Andes. And we put that on top of the Nevada Alsengate mountain at an altitude of about 6,400 meters. And the terminus there of the glacier that descends the flanks of Alsengate is around a similar altitude. It's also just over 5,000 meters. So you have to climb really high. I mean, just to give some context, Mont Blanc, the highest mountain in Western Europe, is about 4,800 meters, the summit. It might be a plus minus a couple of hundred meters, that sort of altitude. We're talking about climbing above, the highest point in Western Europe just to reach the lowest extent of these glaciers. And why are they at such high altitude? Well, you have to climb that high to get cold enough to sustain a glacier. Sea level temperatures are so warm, you have to climb a long way up in the atmosphere to get to freezing conditions. There's also a very high intensity of sunshine at the tropics. That's ultimately what's driving the high temperatures. But it's also an independent pathway for melt. Even if the air is quite cool, you can still have melting occurring at the glacier surface if there's enough sunlight. So, for example, we found on the upper slopes of Mount Everest, which we think are some of the sunniest spots in the world, actually. And the summit may be the sunniest spot in the world. But we find there that you get melting occurring, so melting of the glacier surface at air temperatures that are really, really well below freezing, perhaps as low as -10 degrees Celsius the air temperature may be, but you can still have melting going on at the surface because the intensity of solar radiation is just so extreme. So that's what drives these glaciers or means these glaciers can only exist at these very high altitudes where the air temperature is very low, is to offset some of that solar intensity that's there to drive them out. So the glaciers look different the glaciers are different at lower latitudes in that they're at higher altitudes. They also have different characteristics of when they accumulate and lose mass. So say that these, for example, high mountain Asia, all the activities during the monsoon, but they can also look a bit different when you're on them. In dry environments in the tropics, so these high altitudes, you can get these formations called penitentes, these kind of very clearly defined snow spikes or ridges on the glacier surface that are formed in a very dry environment with lots of solar radiation, and they're driven by sublimation. So the snow surface can look very different too. It can be a key diagnostic of being in a dry, cold, very sunny environment. It can be very difficult to walk on. These penitentes on the Khumbu Glacier, so that descends from Everest, they can be several meters high, and the tops of them in places are wide enough to walk on. In other places they're not. They form a very sharp arête or ridge. And then they also occur at smaller scales. So Nevada Alsengate and the surrounding glaciers, you have much smaller scale penitentes that you can't climb. They might be only ankle or calf height, but they make it quite difficult to traverse or move across glaciers as you lose your footing. So these penitentes are distinct or rather unique or diagnostic of these sunny, cold environments found in the low latitudes. They can look a bit different too. Yes, everything's frozen. The glacier is a glacier, but they can look pretty different.
And what about global warming? The receding of glaciers is, of course, one of the leading concerns related to climate change. And I know that the planet is warming at different rates across the latitudes. So can you explain a little bit about how climate change is affecting low latitude versus high latitude glaciers differently?
Yeah, that's another good question. Glaciers worldwide are indeed in retreat. The vast majority have been shown to have retreated significantly over the course of the 20th and now 21st centuries. And whilst there is difference in the rate, and that's pretty much universal story. Some anomalies include, interestingly, the Karakorums. There's an enormous mass of ice stored in the Karakoram. So the Karakoram run characteristically most notably through Pakistan, and include Gasherbrum, include K2, second highest mountain in the world. And until recently, those glaciers have been shown to be either not retreating or actually advancing. They're known as the Karakoram anomaly. And there's been a fair bit of research into that. I'm not sure the latest consensus, or whether there is now consensus on what was driving that anomaly, but it's unlikely to hold. likely to have been a short-term quirk of the global glacier response. As the climate warms, you have a couple of things happening. You have increased melt rates occurring at lower elevations. You also have less frequent snowfall occurring at lower elevations and more frequent rainfall occurring. So warming hits both sides of that mass balance equation, the inputs and the outputs to a glacier. Hits the outputs, amplifies them by increasing the melt rate, and it also hits the input, the accumulation, by decreasing the frequency of snowfall events. There is some compensation in that a warmer atmosphere does hold more moisture, and that leads to small increases in total precipitation, but it's not enough to offset these other impacts or these other effects, so that being increasing melting and decreasing snowfall. Now, the fastest retreating glaciers in the world tend to be those at low altitude and at higher latitudes, maritime glaciers that are in those locations. And the reason for that is because in maritime environments, so maritime just meaning affected by proximity to the ocean or in close proximity to the ocean, you generally have more precipitation. That means more snow. And the more snow you have, the lower elevation and the warmer environment your glacier can extend to. So some good examples are in Iceland, in Alaska, or the northwest coast of Canada. So these are maritime glaciers that get enormous amounts of precipitation. And I think, for example, on Vatnajökull in Iceland, the snow inputs can reach something extraordinary, like 30 meters a year. I'm not sure if that's a water equivalent or just the depth. We're talking colossal amounts of snow. Listeners may not know where the Vatnajökull ice cap is, but it's in southeast Iceland. It's an enormous mass of ice, the largest mass of ice in Europe, I believe. And it's close to that North Atlantic storm track, that same storm track that causes flooding problems for the UK during the winter, that produces the named storms that we now experience. And those storms, when they're feeding off the warm waters of the Gulf Stream, they can drop really extraordinary amounts of snowfall on the high ground in Iceland. So it generates enormous ice caps. That's why those enormous ice caps are there. It means you can drive ice to really low altitudes because there's such a great supply of it. So it can flow down to these lower altitudes where it's warmer. And then at these altitudes where it's warmer, melt can persist through much of the year. So it might be above zero certainly throughout the summer, but also throughout the transition seasons of spring and autumn. So you can have melting throughout a large fraction of the year. Then if you increase the temperatures, so from climate warming, that increase in temperature is felt, the impact on melting is felt almost year round, because melting is occurring almost year round throughout a large fraction of the year. So where it's warm, already warm, and you have ice, the impact of warming generally tends to be greater because the impact of that increase in temperature is felt over a longer period of time. At higher altitudes, when the melt season is shorter in more continental locations where there's less snow, the impact of warming is felt throughout a shorter period of the year. So the glaciers are generally less sensitive to warming. So that's been a long understood phenomena that continental, so glaciers away from the sea and higher altitudes and environments where there's less precipitation, less snow, they tend to be less sensitive to warming. So by that logic, you would expect tropical glaciers in general to perhaps be less sensitive to warming than these lower altitude, higher latitude glaciers that exist in a warmer climate. But it's a bit more complicated than that because the warming of the atmosphere, because what I was just talking about then was kind of the standardized sensitivity to climate change. In other words, if you increase temperatures by the amount of energy in the atmosphere by a given amount everywhere, by the same amount everywhere, how do the glaciers respond? And what I was describing is that glaciers in generally warmer environments tend to be maritime environments. Those places with more snow will be more sensitive to warming. But the other things taken into consideration is that the amount of warming, or say more generally heating, that's going on across the planet is not uniform through space, and it won't be uniform through space going forward in time. The highest latitudes are generally seeing the biggest increases in temperature, so the Arctic. But now, this goes on to another relatively niche area of research that I'm interested in, but that's only one way of measuring the amount of heat that's accumulating in the atmosphere. Heat can accumulate in the atmosphere, not just in what's called the sensible heat term, which is what we measure with a temperature sensor, so a thermometer, but it can also accumulate in what we call the latent heat term. And that's really, it's proportional to, and you can just substitute the word humidity in here, the specific humidity, the amount of water in the atmosphere. As energy is accumulating in the Earth's atmosphere, you can go into those two terms, those two heat terms. Sensible heat, that increases the temperature you measure with a thermometer, and latent heat, and that's the proportion of the amount of moisture, the mass, the number of kilograms of water in the atmosphere. And it turns out in the Arctic, most of that heat, the vast majority, is going into increasing the temperature of the atmosphere. In lower latitudes, in the tropics, it's not. More is going into the latent heat term, which is the humidity. And glaciers are not just sensitive to the temperature, they're sensitive to the humidity of the atmosphere too. So in other words, glaciers are sensitive to the heat content of the atmosphere. And when we look at heat content, the story is, as I just alluded to, isn't as simple as high latitudes warming fastest. They generally are warming faster. When we look at heat in its totality, rather than just air temperature, tropics are also warming very fast. So those two things combined mean that we should expect tropical glaciers to actually respond a little bit more to climate heating, we'll say, than we would expect if we were just looking at the temperature change of the atmosphere, because heat is accumulating quite rapidly in the tropics, faster when we look at total heat, so sensible and latent together, than if we just look at the temperature response. The issue with trying to establish what's going on, you notice I talk about theory here and which glaciers should respond fastest. We don't have a hugely long record of observation of glacier change in many of the world's regions. So we rely on marker glaciers that are manually monitored around the world to try and figure out what's been going on in the past. And when I say manually monitored, I mean literally bamboo or aluminium stakes drilled into a glacier. And then you go and measure how much of that stake is protruding at different times throughout the year. The more that's protruding, the more ice and snow has been lost. The more that's buried, the more snow is accumulated. And this is known as the manual way of determining the mass balance of glaciers. But it can only be done at a handful of glaciers worldwide. And there's almost 200,000 worldwide. So we have a very, very small sample of the total glacier response. But there are other measures that we can use to try and work out what's going on with glaciers. Remote sensing can track the change through time. You take repeated digital elevation models of glaciers at different points, and you subtract one from the other, and these are generated using satellite remote sensing. You can work out the difference. You can also use satellite measurements to track gravity anomalies in the area underneath the satellites, and that's proportional to the change in mass. So you fly these satellites over glaciated regions and you look at the change in the gravity field through time, and you can work out what's happened to the underlying ice through time. So there are these methods of supplementing the manual measurements, try and figure out what's been going on with glaciers, but they're available. Those records aren't available for very long back in time. Widespread satellite remote sensing we can really date to we've had since about 1980. So relatively brief records. And that's a challenge when trying to answer the type of question that you pose. Which glaciers worldwide are responding fast? In some cases, theory tells us very clearly the direction of travel or which areas should be most sensitive. But when we lack observations of things like the weather and climate in the tropics, and we also lack observations of what's been going on with the glaciers in the tropics, it can be quite difficult to work out what's been going on and what may happen for those very sparsely monitored regions.
Well, I just want to pick up the heat term, the heat idea there, and bring it on to people. I mean, we've seen some record-breaking temperatures across Europe and elsewhere, well, right now or in the past few weeks, but it's been very dry in Europe. What are some of the things that determine how we experience heat?
Yeah, excellent question, and very much related to what we've just been talking about. So we certainly feel the temperature of the atmosphere. And when I say the temperature, as I was mentioning in the last section, I'm referring to what's called the dry bulb temperature. So if you have a thermometer, typically, unless you've deliberately bought something different, you have a dry bulb thermometer. And whenever we talk about temperature, we're talking about the dry bulb temperature. The temperature measured by a thermometer with a dry bulb. It does exactly what it says on the tin. And we are sensitive to variations in that parameter. When the temperature is lower, it feels colder. When it's higher, it feels warmer. And that's because we're exchanging heat with the atmosphere, exchanging sensible heat with the atmosphere. And the rate of sensible heat transfer, in other words, how warm it feels to us, is proportional to the difference in the air temperature and our skin temperature. And for us to be healthy and not succumb to heat exhaustion and then heat stroke, perhaps, we need to maintain a core temperature of about 36, 37 degrees Celsius. And that requires us to have a skin temperature of no more than about 35 degrees Celsius. We use the skin to help us cool. When we're hot, our skin flushes red because of vasodilation. We direct blood flow to the exterior, and that helps dump heat to the environment. So we can dump heat to the environment very easily when the air temperature is below 35 degrees Celsius, because our skin can be at 35 degrees Celsius and be warmer than the air that's blowing across that skin surface. And because the air is therefore cooler than our skin, as it blows across the skin, it cools us down, much like your car engine being cooled down by the fan pulling cooler air across that surface helps regulate the temperature. And it's very easy to keep your engine cool when you're driving fast, right? The faster you go, or the harder the fan works, the more quickly that cool air is taken across the surface of the engine and helps it cool down. So that's quite an interesting threshold, 35 degrees. Once the air goes above 35 degrees, it's warmer than 35 degrees, as measured by a dry bulb thermometer. The air is then warmer than our kind of healthy skin temperature, and it's then a source for us. So we can't dissipate any heat to the environment. And we do need to always be dissipating heat because we're generating heat all the time. Our metabolism, as we exercise, we generate heat, and that heat needs to be dissipated. And we take this for granted. I think it's absolutely remarkable the more you think about it. And I'm not a biologist or a physiologist, but I find it fascinating that this is totally autonomous. You know, you don't have to think about it. Body is regulating internally, shifting these dials and switches to help us keep cool, to direct more blood flow to the skin, to help us dump heat, and also to start sweating to help us dump heat. Because once you go above 35 degrees, you need another mechanism. And actually, in the build up to 35 degrees, you need another mechanism to help dissipate heat. Once it goes above, typically, I think around 27 degrees Celsius, if you're not really doing much, that's a good threshold that you start to need to sweat. And sweating is another pathway to get rid of heat. So to evaporate the droplets of sweat on our skin consumes latent heat. And that heat comes from the heat in your skin. So the feeling you get, and the same thing happens if you've been swimming or you've had a shower and you go outside with wet hair. That cool feeling you have when your skin is wet and the air is blowing across is because the evaporation of the sweat is consuming heat and cooling you down. Now, if we didn't have that mechanism of dissipating heat, we would be unable to dissipate heat to the environment anywhere where the air temperature goes above 35 degrees. It would be an environment in which the heat is what we'd say uncompensable. You can't exist in equilibrium with that environment. Sweating has essentially allowed humans to travel into these environments where the air temperature goes above 35 degrees and maintain a viable temperature without sort of long term. You know, you can exist in equilibrium with the environment. As long as you're well hydrated, you're avoiding extra heat load from the sun, you can exist in these conditions with air temperatures above 35 degrees so long as you can sweat. But of course, there is an upper limit to the conditions that you can dissipate heat through sweating as well. And although we haven't encountered those conditions widely yet, we are approaching heat and humidity combinations where it may not be possible for the human body to maintain a healthy temperature in.
Yes, and you published a paper, or you were a co-author in a paper fairly recently that I think was it documenting the first times this occurred. So where has this happened, and where can we expect it to happen in the future?
Yeah, so I was dangling that carrot out, hoping you'd ask that question. It's the wet bulb temperature that I'm talking about here. So I'll just briefly explain what that is before talking about this particular publication. But I went to great lengths at the beginning of that last question to talk about the dry bulb temperatures, differentiate it from something called the wet bulb temperature. But the wet bulb temperature is, again, quite an intuitive measure from the name. It's a temperature that a thermometer would record when having the bulb end wrapped in a wet wick that's kept wet, and air is passed over that wick and evaporation proceeds. And that evaporation from that wet wick cools the bulb of the thermometer, just like sweat from our skin cools the surface of our skin and helps us maintain a healthy temperature. Now, if I said, as I alluded to or mentioned in the last question, we need to keep our skin temperature no warmer than 35 degrees in order to keep our core temperature at a safe level. Now, when the wet bulb temperature goes above 35 degrees, that's an indicator that our skin temperature, even if covered in sweat or water, would rise above 35 degrees. So the wet bulb temperature is taken as a good indicator of how hot it feels in general. And this limit, or this value of 35 degrees, is taken as the upper limit that humans can tolerate in equilibrium, I would say, is a good way of describing it. So in other words, once it goes above 35 degrees, the wet bulb temperature, human has no way of keeping the core temperature at a safe level without some kind of external cooling mechanism, be that the ingestion of chilled water or blowing artificially cooled air across your skin. So, for example, through air conditioning. So this wet bulb temperature of 35 degrees is essentially taken as the upper limit to human heat adaptation. So once it goes above that value, very bad consequences for human health could be anticipated if humans exposed to it had nowhere to go, can retreat to cooler conditions, and that heat and humidity combination was sustained. And so the next question is, well, where experiences such extreme humid heat? And until our study in 2019 now, or it was 2020, it was thought that nowhere had experienced such extreme human heat and humidity. There was a landmark paper published in 2010 by Sherwood and Huber that first shed light on that threshold from the climate sciences perspectives in the context of climate warming, recognizing that it can get so hot and humid that it doesn't matter how fit and healthy you are, a human can't endure those conditions. So Sherwood and Huber should be and are recognized as recognizing that 35-degree wet bulb limit from the climate sciences perspective. And the question they asked is, where has experienced this type of heat and humidity in the past, and how much global warming would it take until humans could be expected to have to endure such or confront such extreme heat and humidity? And their conclusion was that looking back in time, humans hadn't likely experienced such extreme humid heat ever. And they also concluded that it would take quite a lot of warming until large regions were likely to encounter such extreme humid heat. So, for example, around 10 degrees of warming would be required to push a large fraction of the tropics across that deadly threshold. And I'll just call this threshold the deadly threshold from now on. And then subsequent studies used higher resolution models to ask that same question: how much warming might be required until regions start to cross this deadly threshold? And they zoomed in on the hottest places worldwide, starting with the Persian Gulf region. And then I think we had Southern Asia next. So that was Pakistan, India, Bangladesh. And then the North China Plain is the third in this series, looking at how much warming was required to cross the deadly heat threshold. And they're all fairly similar in their conclusions, actually, these three studies by the same research group that found once you get to about 4 degrees of global warming, it becomes possible to start sending relatively large regions, so for example, entire cities, over this deadly threshold. Rarely, but let's say perhaps a couple of times a decade would be a reasonable expectation. So that's about 4 degrees of warming. It starts to happen in the hottest, most humid parts of the world. It would be a more common incident than the likes of the 40 degrees that the UK suffered or endured earlier this summer, but it wouldn't be vanishingly rare either. And then the question we asked in the relatively recent study that I was involved in was, well, when you zoom in even further, so you go for the Huber and Sherwood scale, was looking at kind of hundreds of kilometers by hundreds of kilometers. That's how a region was defined. So using that sort of minimal unit, spatial unit, to say has anywhere experienced such extreme heat. Moving on to the more recent work by researchers in the US, the question or the tools they were using involved models that had scales of sort of horizontal resolutions of tens of kilometers. And they said, well, you don't have to see as much global warming to start encountering such deadly humid heat. 4 degrees rather than closer to 10 degrees. So the more you come down in or go up in resolution, the more pressing this threat of really deadly heat seemed to become. So the question we had was, well, what happens if you go to the scale of individual weather stations worldwide and you look at individual hours worldwide in the observational record? How close have we got? How close to the hottest and most humid places on Earth come to this deadly threshold? And it turns out some places have crossed that threshold, albeit for very short periods of time, so individual hours, and we're talking about only a handful of spots. And I mean, off the top of my head, I think it was 3 or 4 weather stations worldwide have crossed that threshold on more than one occasion. And we are looking at places around the Persian Gulf, so the UAE, Qatar, and in the Indus Valley in Pakistan. So it's around that region, the Persian Gulf region, the Indus Valley. They are the hottest and most humid spots on Earth. And they have already crossed this line very briefly. And it was a real challenge quality assuring those records. If you ever work with observations, you know that a whole host of things can contaminate a measurement, be it heating of the sensor by the sun. That's no longer recording the air temperature. It's recording a combination of the air temperature and the solar load. Malfunctions in the sensor, misreading of sensors from manual stations. So what we did was put the data through really rigorous quality control procedure, and it included cross-referencing the simultaneous measurements that were taken from ships sailing in the Persian Gulf. And as part of that process, we found some really extraordinary things. The sea surface temperatures had routinely gone above 35 degrees in the Persian Gulf from individual spots, which is kind of the lowest temperature you need to potentially sustain air temperatures. with wet bulb temperatures in the atmosphere of 35 degrees. So we found consistency and support regionally for those extreme wet bulb temperatures from a physical processes point of view. So we have quite high confidence in standing over those individual hours and saying, yes, they are short-lived, and yes, they are very localized, but they have occurred. To the best of our understanding, they have occurred. And yet they haven't affected large regions yet for long periods of time. And that's the big concern, that we still haven't seen the effects of a heat wave in which extreme humid heat crosses that deadly threshold, where lots of people are present, so in a big city, and for a relatively long period of time, so more than just an individual hour or two, but perhaps a 6 or 12-hour period, perhaps for a whole night. And that's the big concern I have as a researcher, is what does that mean when that occurs?
You've just brought up the kind of the question I was going to get to. I mean, I'm not sure if you read Stanley Robinson's book, Ministry of the Future, where he opens with a scenario in quite a lot of detail that's one of these events, but over a large swathe of India, kills tens of millions of people. Is this something we should fear? Is it quite likely on the course that we're on, or is it a matter of bad luck? Something extreme could happen.
Yeah. Well, it's a very, very good question, and one that I have spent a lot of time thinking about. And I have to sort of declare that I'm a climate scientist, not a physiologist. And also, I think there's a fair bit of need here for imagination. I think Stanley Robinson did a great job. I read about 60% of the book. I read the beginning because of the descriptions I'd heard elsewhere. So for readers, again, listeners that aren't familiar with the story, the beginning, so the setup for the book is this deadly heat wave, this deadly humid heat wave in India, where the wet bulb temperature exceeds 35 degrees for a long period of time. And yeah, it kills millions, doesn't it? And it shapes everything that comes. The protagonist was involved in the heat wave, is highly traumatized. I don't want to ruin the story, but goes on to do some fairly unpleasant things. And I think there's a place for that kind of imagination, actually, because we don't know what would happen if a wet bulb, a humid heat wave occurred of the like described in that book. And I don't think anyone can know exactly what would happen, because it's a first. History is an interesting guide, and what happens during, we can mine the history books to see what happens during extreme or unprecedented heat. So, for example, we don't have to go too far back in time to see some really devastating heat waves, including some very close to home. In Europe in 2003, around 70,000 people were killed from the very extreme summer temperatures that were witnessed that year, mostly in France, and it was mostly the elderly that suffered. And in care homes too, a very unfortunate summer indeed. And then in 2010, we saw probably around 50,000 people killed in Russia from, again, a compound extreme, but it was extreme heat and also a very poor air quality. So we don't have to go far back in time to see sort of mass mortality events from extreme heat, but we don't have any guide to the types of conditions that we're talking about that loom large in the future. And that is these heat waves that, and I know it can be easy to gloss over the significance of what they represent. But for a healthy human, so we're talking about, let's say, an Olympic athlete, someone who's, an Olympic endurance athlete, exposed in one of these heat waves. Let's make it even more compelling and say an Olympic endurance athlete from one of the hottest countries on Earth, exposed to a heat wave in which the wet bulb temperature goes above 35 degrees. They still are overheating in that heat wave. And if they're not wearing anything, they're well hydrated, and they've got a dozen fans on them. The type that blow air, not that cheer for you. But if you have all of that, you're still accumulating heat. You're still overheating. It's an issue of thermodynamics. You can't get rid of the heat. It's just a matter of time until this elite endurance athlete succumbs to a heat-related illness. If they're exposed to those conditions indefinitely, it's simply a matter of time until they succumb, unless they've got another way of cooling themselves. And humans have never encountered those sorts of conditions beyond in steam rooms and in saunas. So what happens when you expose, lots of people to those conditions? I don't know. It wouldn't be instant. It's coming to a heat-related illness. There's a period that the body can weather those conditions for. And also the threshold is clearly more fuzzy in reality than it's treated in a climate research context. Some people, depending on what you're doing, how much heat you're generating, if you're walking, if you're sitting, etc., will depend on where that threshold is of heat accumulation. That threshold of inevitable heat accumulation versus being able to dissipate heat and keep a temperature at a safe level. It's a fuzzy threshold in reality. So it's not as clear as presented in climate research sometimes, and also in the Stanley Robinson book. You can expect these impacts to emerge at much lower wet bulb temperatures. And already we see them in extreme episodes of humid heat mortality rises well before you get to that threshold. But there is something fundamental about that threshold too. It's this upper limit beyond which no human can maintain a safe temperature. And we just don't really know what happens on the ground when those conditions are crossed and lots of people are exposed to them. The next question, so that all sounds very dire. The next question is, well, how much global warming does there need to be for this to be a possibility? And I've already alluded to a few studies that have said maybe around 4 degrees of warming and relatively large regions can start to cross this threshold. And there was a really nice study, I think it was in 2021, published in Nature Geoscience, that brought a bit of order to the chaos and put out a really nice big picture climate perspective on the controls, how much warming you need to see until large regions indeed cross that threshold. So it was kind of a big picture perspective on that same question. How much warming do we need to see until large regions are likely to go across the deadly wet bulb temperature of 35 degrees? And they found an interesting constraint, or they presented an interesting constraint. Actually, Scher and Huber had mentioned or performed some investigations towards in that 2010 paper. And that is, it's the tropical sea surface temperatures that are the limit. The highest wet bulb temperatures in the tropics are linked to the highest sea surface temperatures in the tropics. Once they approach 35 degrees, then large regions are susceptible to crossing that threshold. So it's a pretty good and convenient metric to see how likely we are to cross that threshold is what are the tropical sea surface temperatures doing. And we're a fair way away from 35 degrees for the hottest tropical sea surface temperatures. And things settle out, I recall, testing my memory, but about the same answer. We're looking at upwards of 4 degrees of global warming until you can expect larger regions to cross that 35-degree threshold. What we're talking about in the observational study, where we notice individual regions, and what some of the other groups are identifying is more local processes in the subtropics that can generate really extreme humid heat, short-lived extreme humid heat. And it's important to really resolve exactly what those physical processes are that can generate those extreme local conditions of extreme humidity in the subtropics. And there's work to be done there, but large-scale regions in the tropics are likely not going to go above that 35-degree wet bulb temperature until tropical sea surface temperatures, the highest sea surface temperatures, cross that threshold. That's a fair way off, and it's a very, very strong incentive, to stay a long, long way away from anything that looks like the RCP 8.5 warming scenario. Anything that gives us upwards of 4 degrees of global warming. The tropics become, just from a heat point of view, pretty dangerous to live in, and very much at risk of the type of scenario that Stanley Robinson explores. I think there's real value in trying to understand what on earth could be going on the ground during a heat wave in which you see a large region exposed to those sorts of conditions. It kind of falls at the edges of lots of different areas of research expertise. It's not a climate question. It's not really a physiology question. It's a social systems question and sort of a new territory question. How do people respond when faced with a threat like that?
How can we respond as such a threat approaches, at least? I mean, we're not at 4 degrees warming, we're at about 1.1 or so. But there's evidence that climate change is causing not just greater average temperatures, but in particular, greater extreme temperatures. How can the human societies, in particular, the human societies that exist at low latitudes right now, adapt to extreme warm temperatures?
Yeah, that's an excellent question, because already, heat kills a lot of people around the world a year. Extreme heat does. And as I mentioned, we had this real horror show in Europe in 2003 with upwards of 70,000 people killed. And in response to that, and actually it's pretty timely that we're doing this podcast in the week that we have a heat health warning issued for England from tomorrow onwards until the end of the week, because temperatures are forecast to exceed 30 degrees and actually reach, I think, as high as 35 degrees Celsius in southeast England. And this speaks to the fact that society can do quite a bit to reduce the impact of extreme heat. These heat health early warning systems use the best forecasts and also innovations or other developments in public messaging to help reduce the impact of extreme heat. So to prepare people well in advance and issue them with sensible health guidance for how to minimize the impact of extreme heat, doing things like staying out of the sun, decreasing physical activity, drinking water, turning off household appliances at home, ventilating your home properly to try and reduce the impact of heat. So that means doing things like opening the windows in the small hours in the morning or at night, keeping the curtains closed during the day, can reduce indoor temperatures by, several degrees and reduce the impact of extreme heat accordingly. And in Europe, we've had similar episodes of extreme heat to the 2003 disaster, but we haven't seen the same levels of casualties because of these heat health early warning systems. So there's lots of evidence that suggests that they do work. So these relatively simple measures, from making sure forecasts are properly communicated and also the right advice is given alongside those forecasts to help people reduce the impact of heat on their lives, that can save lives. There's also talk that, the field is always progressing, of naming heat waves in the same way that we name storms so that people recall them. The reason why we name storms is that we connect quite readily the name of the event with the impact. We find that easier to do than to talk about a low pressure system that occurred on, let's say, the 12th of February 2014. If we call it the St. Jude's Day storm, that's going one step closer to committing to memory. I'm not sure if that is St. Jude's Day, but in any case, attaching a name like Alvin or something else beginning with A or B, etc. And same when we name tropical cyclones, they become more memorable. Doing the same thing with heat is being talked about now as helping in that process. Otherwise, it can be quite difficult to recall the impacts of extreme heat events and also to perhaps characterize them right in our memory. Heat waves are far more diffuse than a storm in terms of the way we experience them. A storm has a clearly defined beginning and end and does things that we see quite quickly. Although quite clearly a heat wave is just different fundamentally. A lot of the things that we associate with a heat wave are enjoyable, perhaps the nice mornings, sunny commute to work, eating ice cream outside. But later on in the afternoon, so in the course of the same day, the weather can turn from a friend to a foe and can really pose a threat to our health. So attaching names to the heat waves is sort of the next thing that's being discussed. But this is all quite restricted, or what I've spoken about so far has been relevant to Northwest Europe and to the US and North America to some extent too. So that's developing these heat health early warnings and watches to preserve life. The most extreme heat on Earth is experienced in the tropics and subtropics. And interestingly enough, the tropics and subtropics have not seen the deployment of these heat health early warning systems to the extent that we have in the mid-latitudes in Europe and North America. And in fact, the first heat health early warning system deployed in South Asia was deployed in South Asia in 2014, so quite recently. And that was in the Indian city of Ahmedabad. Again, devised or made up of similar measures. So, being the good integration of forecasts with public awareness campaigns and doing things like keeping open public spaces where people can access water to help cool themselves down, be they bathing facilities, fountains, etc., giving out water for free to people, clean water to help them stay hydrated. And so those measures can go a long way. We've seen them do good in the mid-latitudes in Europe and North America. They're only just starting to be deployed in the places that are most on the front lines, the hottest and most humid places on Earth, so the likes of South Asia. So lots of lives can be saved by just accelerating that process, deploying those early warning health watches and warnings to those regions. Lives can be saved that way. But we also have to recognise that there is a limit as to how far those types of measures can go. They can't help very much with the likes of the crossings of this 35-degree wet bulb threshold that we've discussed. And in an episode like that's hopefully, as you say, and as we've discussed, a very long way off, and hopefully in a world that we don't encounter for millennia to come. But in a world that we start getting close to that threshold, behavioural modifications can only do so much, and they can't help us beyond that threshold. So we perhaps need to be more creative in our thinking in the hottest and most humid parts of the world with respect to what we do during those episodes of really extreme heat. Like, for example, the wider availability of cooling centres that do have air conditioning supplied to them in a way that is resilient to pressures on the electrical grid. It may be, what I'm saying is, in some heat waves, they might be so extreme that the only way for people to weather them is to go to a cooler space, a space that is artificially cool. Now, in general, people tend to turn on air conditioning during heat waves anyway. If you live in a country where the energy supply is extremely reliable and has great scalable capacity, then that can be a viable solution to weather these short-term storms, even in a world in which we need to use air conditioning less because of the impact on emissions it has. But in large parts of the world, turning on the air conditioning during the heat wave can lead to a brownout, can actually kill the electrical supply for everyone as the grid is overwhelmed. So it can mean that when you need energy most, it's least available. So relying on air conditioning to weather these storms is an unreliable strategy at present in some of these hottest and most humid places worldwide. So going forward, as the heat waves challenge human physiology more and more, what I'm saying is there's less scope for behavioural modification to decrease the impacts or to stave off the impacts of extreme heat. So in those places where that capacity is really decreasing, we need to look at things like cooling centres where people can retreat to. There's reliable air conditioning to act as a source of protection. It's still a high stakes game because if the air conditioning fails, then you are indeed in trouble. But in some parts of the world, we're going to have to rely more and more on artificial cooling mechanisms to help people weather the storms. And hopefully there's innovation to come there to help people cool in perhaps, what I'm thinking about is equivalent of hurricane evacuation centres, but for heat. We're going to have to start thinking about heat more and more in that way.
So we're looking at a present that's already warmer than the past. There's justifiable concern that in upcoming years and upcoming decades, these heat extremes will be worse and worse. To a great degree, depending upon emission scenarios, by the end of the century, could really be quite severe. Like so much talk of climate change, we're debating different possible futures, none of which sound particularly pleasant. What gives you optimism in this world, in your work and in climate change?
Yeah, that's a very profound question, isn't it? You sum that up quite well in that we are choosing between options for the future. None of them are particularly palatable. But when I say none of them, I mean we're going to see more warming. It's how much more warming we see that we're choosing between. And ultimately, what I take optimism in is that where I find optimism is that we're in a position to do this. I think we take this for granted and overlook this quite often. But you think about how long humans have been around for. So about 70,000 years since the Great Leap Forward, mass movement out of Africa and the emergence of things that start to look like culture in different parts of the world. Human civilization being around 10,000 years old. And when I say civilization, I'm talking about our agricultural societies. So we've got this long line of human history, and we stand here now having built upon, granted, most of the progress in scientific inquiry and capacity has happened in the last few hundred years, but we stand here in a position where we can, for the first time, really see what the consequences of different decisions will be. And we can see that we understand decisions we make today will shape the surface of the earth, the coastlines of the world for thousands of years to come. So it's an enormous kind of weight that's on our shoulders. But also, I think it's remarkable that we're in this position where we, building on this collective or progression of scientific thought, inquiry, the tools that are available to us, we are in a position to see the consequence of our actions, to have a preview of what the future holds. And we do care about it. We beat ourselves up on, and I think rightly so, that there hasn't been consensus on what to do for a long time. But humans are innately competitive with one another. We have some level of, this is some of my worldview is leaking out here, less about, my expertise as a scientist and just my general views on the world. But we're innately competitive with one another. There's nothing in our DNA that necessarily means we should, choose to bother ourselves with the concerns of people that we've never met, either distance in space or in time, so generations away from us. But enough people do care that we've come together as a world and we've assembled and laid out these commitments, these pledges that we will try and limit warming to no more than 2 degrees, aspirationally to 1.5 degrees. Most of the world is on board with that. And well, granted, it's not enough to fix the problem. And I think there's so much to do that, I don't want to be seen as or heard to be underestimating the scale of the challenge. We're nowhere near where we need to be. We know the scale of the task ahead if we're to limit warming to 1.5 degrees. It's colossal. But I think we can pause just a moment to appreciate that we are marching in the right direction, not quickly enough, but it could be so much worse. I'm optimistic because of the way humanity is coming together and is trying. The further we get down that path, the greater the progress in limiting warming to 1.5 degrees, the better the world will be. Each fraction of a degree matters. So I think kind of reflecting broadly and philosophically, I think it's a remarkable testament of human cooperation that we are where we are, actually. It's profoundly sad that humans are innately wired to cooperate and see things from this kind of the bigger picture context. If we all saw the bigger picture context and we're operating in the interest of one humanity, then we would never have wasted so much time. The problem would be solved. But that's not what humans are. We are, as I say, we have some level of innate competitiveness within us. And we're working as individuals, as groups of individuals, and as groups of individuals, and we are making progress. We are stepping forward in the right direction, not fast enough yet, but I take great delight that we are starting to move in the right direction, and every degree matters. And it no longer looks like 4 degrees is realistically on the table. Let's say it doesn't look like the most likely outcome anymore. Of course, it's on the table. It doesn't look like the most likely outcome. And that's tremendous. That's changed in the last, decade or so. That was the case where we were marching alongside in step with the RCP 8.5 scenario. That now looks like very much the worst case scenario and shouldn't be on the table. So slightly roundabout answer there, but I think the fact that we're working together in the way that we are is remarkable. It's not enough, but when you consider what humans are, it's remarkable, I think. It's personal opinion.
On that note, we'll wrap up. This has been Dr. Tom Matthews of King's College London. Tom, thank you for joining us on Challenging Climate.
Thanks very much, Jesse. It was a pleasure.
Yeah, thanks for joining us. That was great. Well, thanks for listening. Please rate or review us on Apple Podcasts and elsewhere, and consider supporting us on Patreon. That's patreon.com/challengingclimate.